Hi guys, in this video we are going to talk about the Chatelier principle. First of all, we need to know what is the definition or what is the meaning of the Chatelier principle. Now it states that if we have an equilibrium system and there is a change acting on the system, then the system will respond. But it will respond in a way in order to counteract or minimize such a change. Now let's look at this particular example. There is a very simple equilibrium system where reactant R reacts to form product P, and this is a reversible reaction. If you look at this graph, which is a concentration time graph, now you notice at the beginning the concentration of reactant and product is not changing because it is an equilibrium mixture, right? Now let's just say at this particular time we add a small amount of R into the mixture, and you can see at the moment where R is added, the concentration of R increases significantly, right? Now this serves as the change that occurs on the system, right? The change is that the concentration of R increases. Now according to the Chatelier principle, it will respond in order to counteract such a change. So to counteract the increase in concentration of R is obviously to decrease its concentration, right? So as you can see, after it is being added, the system is no longer at equilibrium, and it will adjust itself in order to reach a new equilibrium where you see again the two concentrations remain unchanged. Now as you can see that when they change to reach the new equilibrium, they change by lowering the concentration of R, and as the concentration of R is decreasing, the concentration of product obviously increasing, right? So after they reach the new equilibrium, you notice that the concentration of R has been significantly lowered when compared to the moment where the R is active. So this illustrates the counteract, as predicted by the Chatelier principle. So we say that after we add R, in order to consume the R, you must have a net forward reaction, So we would say that the equilibrium shift to the right, shift to the right, or shift to the product side, okay? So that means you will have a faster forward reaction than the backward reaction, okay? Resulting in a net forward reaction, okay? And this is how the equilibrium responds. We will use the equilibrium shift to the right, or equilibrium position shift to the right, okay? Now, you also notice another thing is the change, the extent of changes. Now you notice this is the moment where R is added, and this is the part where the new equilibrium is reached, and there's altogether X amount of R being consumed during this period of time, right? And because the mole ratio is 1:1, so you will expect to see also same amount of product form, okay? So this is another thing I want you to pay attention to. Now the third thing, the first one is the equilibrium position changing. The second one is the extent of reaction or the extent of changes. And the third thing is about the new equilibrium. You notice that even though you are successfully lower the concentration of R, at the end of the day you still have a higher concentration of R when compared to original. Now this is what we call what's done is done, right? Because you have added the R, you cannot completely remove it, right? What's done is done. So what the system can do is to counteract in order to minimize the change, but it doesn't go back to original. So pay extra attention that if you are asked to draw this graph, make sure that at the new equilibrium, the concentration of R should be higher than original, right? Because yeah, we have added some R. It has to be an increase in R concentration at the end of the day, okay? So these are the three bullet points that I have just explained it, so you can go through the words yourself. Okay. Now, over here we have a practice question. Now again, whenever we have a practice question, I expect you to pause the video and try it, or at least go through it yourself first before looking at my explanation. Now I assume you already finished your, you have tried out or at least read the question, so let's discuss. Now we have an equilibrium system like this, and we have at an equilibrium situation, we have 0.2 mole per dm cube of this particular product, the complex ion, let's put it down, okay? And then we have 0.5 chloride ion, and then we have 0.3 m of cobalt 2 ion. Okay, let's put it down. Okay. Now, at this to this equilibrium mixture, a student add this amount of sodium chloride, okay, into the solution. And I haven't included the volume of the mixture. Let's just say this is 1 dm cube, okay, for simplicity's sake. Okay, the total volume is 1 dm cube. Okay, that would be easier for us to tackle the question. Now, the first part, explain how the equilibrium position and the equilibrium constant change when we add the sodium chloride. Now, the first thing you have to mention is what is the change? What is the change? Because the Chatelier principle starts with a change. If you don't know the change, how can you predict the response, right? So the change is the chloride ion concentration increases. Okay, the chloride ion concentration increases as you add the sodium chloride. Now, so when the concentration of chloride ion increases, according to the Chatelier principle, the Chatelier principle would say that, oh, I want the chloride ion concentration to decrease, right, in order to counteract the change. Now, to do that, we have to shift the equilibrium to the right-hand side, okay, to the right-hand side, to have a faster forward reaction so as to consume more chloride ions, right? So that makes sense. So this is what we're going to write down next about the equilibrium position. So the equilibrium position, okay, will shift to the right, okay, thus consuming more chloride ion, okay, so counteracting the change. And the third one is about the Kc. So if you remember, equilibrium constant is temperature dependent. That means only when a temperature change, otherwise Kc is kept constant. Okay? So in this case, did the temperature change? Of course not. So the Kc remains unchanged as temperature is constant. Okay, so this is how you answer this part. Now for part B, it is more challenging because you have to express the concept in form of a graph. Okay, so now this is the point where the sodium chloride is added. So let's just illustrate an equilibrium mixture before the change had happened. So basically we have to follow these concentration, and I also follow the color. Actually this is blue in color and this is pink, and that's why. So this one is 1.2 m, right? So let me put it down here, 1.2 m over here, and this is the reference point. This is where the change occurred. And then I can have the chloride ion, 0.5 over here, and then I had the cobalt 2 plus, which is 0.3 over here. Okay. Now upon the addition of 0.5 mole of sodium chloride, now because I said it's 1 dm cube, so the concentration should change to 1 mole per dm cube, right? 1 mole per dm cube, right? Okay. So all of a sudden here, the concentration of chloride ion jumps to a very high concentration. Okay, so according to the Chatelier principle, we want the concentration to decrease. So This one will slowly decrease until they reach a new equilibrium, probably at around this point. Okay. So this is the chloride ion concentration. Now, as chloride is being consumed, the cobalt 2+ is also being consumed, right? Both of them are reactants. So this one will also decrease in concentration, but pay attention. You need to tell the invigilators that you understand there is a stoichiometric relationship. So it's 1 to 4, right? So if there is a huge decrease here, so this one you cannot have a similar decrease, otherwise it does not fit with the stoichiometry. Should be 1 to 4 ratio, right? But it's just a sketching, so you don't have to really measure using a ruler, but at least you have to tell that you have to show your understanding on the stoichiometry. Now this one is the product which will increase, okay? So it will increase a little bit and then they reach equilibrium afterwards. Okay, so this is what we expect to see as the graph, okay, to show the change upon adding sodium chloride. Okay. Now, like I said, the Chatelier principle help us to predict changes when there is, help us to predict how the system responds when we have a change. But what kind of change are we talking about? In DSC syllabus, we are focusing on 3 major changes. They are the concentration, and then temperature, as well as catalyst, okay? And we are going to talk about each of them in detail. Now, first, let's talk about concentration. Under the category of concentration, there are a couple of ways that we can change the concentration. So first of all, it's very straightforward. We add or remove any reactant or products. The second one is related to gas, related to gaseous system, okay? More of a gaseous system. Because in gaseous system, we don't have a solvent, we don't have water, right? So when we look at the concentration of gas, usually we can look at the pressure. Look at the pressure. So the higher the concentration, the higher the pressure. Okay. By changing the volume, it can also affect the pressure. Okay, because with a smaller container, you will have a higher pressure, right? So the second one is mostly concerning about gas, and the third one is of course deal with aqueous solution. Okay. Now let's look at the first situation. So we have a reaction like this. Now think about it. If we add some hydrogen gas, then the concentration of H2 increases. So the Chatelier principle will expecting the H2 to decrease. To decrease the concentration of H2, it has to shift the equilibrium to the right so as to consume more H2. So this one is very straightforward. Okay, you will expect to see a net forward reaction consuming the H2. Now the second situation is a little bit more complicated. It has to do with the volume and pressure. Now there are also a couple of ways we can mess with the pressure. One way of doing this is to decrease the volume or increase the volume. Now in this case, we try to focus on the increase in pressure here. So to increase the pressure, you decrease the volume. So imagine you have a movable piston here. When you press down the piston, you are increasing the pressure inside the container. Okay, so volume decreases, pressure increases. So this is one way of changing the pressure. Another one is to increase the amount of gaseous reactant or product because with more gas, they will heat the container wall more frequently, and the reaction force given by the container wall is actually contributing to the pressure. So therefore, the more the gas, the higher the pressure. This is the idea. Obviously, adding a gas will increase the pressure because you got more collision. Okay, but there is another situation where we add an inert gas, okay, a noble gas, a gas that is not part of the system. Now, in fact, the third one has nothing to do with the equilibrium system, simply because it is not part of the system. So the third one all you have to know is if we add something that is not part of the system, which is not affecting the system, regarding to any of the chemical species, then they actually do not affect the equilibrium position. So basically we focus on the first two. Okay, let's just say in this situation where we press down the piston, so lower the volume and increasing the pressure. Now the system, now the pressure increases, right? Pressure increases. So the Chatelier principle, of course, it wants to have the pressure decrease, right? So how can they do that? How can they do that? All we have to do is to lower the pressure by increasing the number of mole of gas. Okay? Because like I said, if you have more gas, then the pressure increases, right? Now the Le Chatelier principle states that it wants the pressure to decrease. Sorry. So another way around would be less gas, then the pressure decreases, right? So Le Chatelier principle wants the pressure to decrease. So basically, it wants less gas. So how can they get less gas? Well, it is by shifting the equilibrium to the side with less gas. In this case, you can see that there are 1 plus 3 equals to 4 mole of gas on the left and 2 mole of gas on the right. So obviously, the right-hand side is the one with less gas. So in order to fulfill what the Chatelier principle predicts, the equilibrium will shift to the right. Okay? So that there will be less gaseous molecules, right? And therefore, the pressure will decrease, okay? Which counteracting the change. So this is the idea. So basically, if you have an increase in pressure, you shift to the side with fewer molecules, okay? This is the idea. Now, this is the part where it refers to the addition of inert gas, which because it is not part of the system and it does not affect the concentration of any of the chemical species within the system, and therefore it does not affect the equilibrium position, not to mention about Kc. Alright, so this is the idea. Now, the third situation here is about dilution. Now, there are two ways of explaining how it works. Now, first of all, think about what are the changes that actually occur when you dilute something. Let's just say there is a 100 cm cube of mixture, and then you add an extra 100 cm cube of distilled water. Like, what is the change? Now, of course, the change would be both reactant and product would be diluted. So the concentration of everything decreases by half, right? Decreases by half. So, according to Le Chatelier principle, of course, they want to regain the concentration, right? Regain the concentration. So, one way of thinking is, you can think about the whole system, everything are solute. Okay, this is a solute, this is a solute, this is a solute. Okay? If you're diluting the whole system, the total concentration of solute decreases. So, Le Chatelier principle wants the total solute concentration to increase. Okay, let me put it down. So, the solute concentration decreases, and LCP wants the solute concentration to increase. So, to do that, they want to shift the equilibrium position to the side with more solute. So, in this case, which side has more solute? Well, here I see only one species that is an aqueous state, but here we have two, right? So more solute on the right-hand side. In that case, it will actually shift, okay, the EQM to right, okay? So we got more solute, okay? So the concentration of solute increase, that counteracts with the solute concentration decrease at the first place upon dilution, okay? So this is one way of thinking. Another way of thinking is we make use of the equilibrium constant expression. So Kc equals to CH3 COO minus H3O plus over CH3 COOH. Now pay attention that water is a solvent, it is not part of the equation. Alright? Now think about it. If we, like I said, if we double the amount of water, then everything will have its concentration decreased by half. So upon dilution, then we will expect to see this one, right? Decreased by half. Decreased by half, right? So you realize that because at the top there are 2 concentrations altogether. So there's actually 4 times decrease in concentration. Okay, so so basically the products are more diluted than the reactant, right? We can think about it this way. It's more diluted than the reactant. So the equilibrium will shift to the product side in order to replenish the concentration of the product side. Okay, there is a 4 times decrease in concentration, and there are 2 times. So of course we have to move back to the product side, okay, to help out with the concentration. So this is one way of thinking. Now you may think about how do we explain it in exam? Well, actually, Le Chatelier principle is not for explaining anything. Like, this is not a law, this is not a theory. It is only a tool that is very convenient for us to predict the changes, So even in the exam, what they expect you to do is to qualitatively predict. It does not really ask you to explain using the Chatelier principle. Okay? So that means in the exam they won't ask you to explain using the Chatelier principle because it is not an explanation, right? Now, so we are finished talking about concentration. Let's move on. Well, we have a practice question here, so let's have a look. Again, pause the video and try it yourself first before looking at my answer. All right, let's get started. So this one, we add small amount of silver nitrate. Now you know silver nitrate is going to remove the chloride ions, right? So basically it lowers the concentration of chloride ions. So of course it will shift to left, okay? Shift to the left, okay? And what about equilibrium constant? And actually, if you're smart enough, you realize that among all these changes, there is no change in concentration, so everything will remain unchanged, okay? Everything remain unchanged. So here, shift to the left. Now here, if I add small amount of the product, then of course they want to consume the extra product by shifting to the left. So shift to the left, okay? Here, if you get rid of the ammonia, so there's a decrease in concentration of ammonia, so it will shift the equilibrium position to the right. If you increase the volume, so increase the volume, that means pressure decrease, right? With lower pressure, the Le Chatelier principle wants the pressure to increase, right? So you want to shift the equilibrium to the side with more molecules, right? More gaseous molecule. In this case, the left-hand side. So it will shift to the left, okay? Now, argon gas has no effect, like I said, because argon is not part of the system, and it does not affect the concentration of any of the species within the system, and that's why. Okay, so down here we have a question, a very classic question, where we have this particular system, and so they are put into a syringe, okay, with the mouth sealed off, okay, like this, and we have the gas inside. Now the gas originally should be pale brown because you have some brown thing plus some colorless thing, so they are pale brown. So it should be brown or pale brown, doesn't really matter, okay? Now state and explain observations when the piston is pressed down. Now you notice there are 4 marks because there are 2 observations. Now first of all, as you press it down, then, okay, I try to draw this one out. You press down the piston, okay, like this. You should expect to see the mixture becomes more brown, okay, more brown, okay? Simply because when you press down the piston, the volume of the container decreases. So all the color, the NO2, is forced to pack more closed. So if the brown thing becomes more closely packed, they appear more brown. Okay, so this is the first observation. So the first one is more brown, okay, upon the piston is just pressed down, okay, because, right, the the concentration of NO2 increases immediately. Okay? Now the second thing is, so after some time, if you give them some time for the equilibrium to re-establish, because remember, the equilibrium takes time to establish, right? So if you provide sufficient time, okay, should be here, then the gas should be less brown, okay? Should be less brown, okay? So less brown, okay, after some time. Now why is that? Because, think about it, when you press down the piston, you decrease the volume, so you raise the pressure. So the pressure increases, right? So the Chatelier principle wants the pressure to decrease, right? Wants the pressure to decrease. So they want to shift the equilibrium to the side with fewer molecules, in this case the product side. So we will say, so when shifting to the product side, which is the colorless N2O4, this is the reason why the color becomes less brown afterwards. Okay, so because the equilibrium position shift to the right, okay, consuming more brown NO2 to produce more colorless N2O4. Okay, so that would be the answer. Okay, C, why the nozzle must be sealed? So we need to have a closed system. Okay, we need to have a closed system. Okay, prevent substance from escaping. All right. So just one precaution, of course, in the fume cupboard, fume hood, because NO2 is toxic. Okay, so that's the idea. Now move on to the next effect, which is the temperature. Now temperature, there are three immediate effects. First of all, whenever we have a higher temperature, then we know that the molecules or particles collide more frequently. So the reaction will be faster. Now this is true for forward and backward reaction. So at a higher temperature, forward and backward reaction are both become faster. And therefore, it takes less time. It takes less time to reach the equilibrium. And vice versa. Of course, if you bring down the temperature, it takes a longer time to reach equilibrium. Okay, so this is the first thing about the time it takes to reach equilibrium. Now the second one is about equilibrium position. Now this one we have to do with the whether or not the reaction is exothermic or endothermic. Now think about it. If there is a system like this and it says delta H is negative, that means the forward reaction is exothermic. Now if the forward reaction is exothermic, then the backward reaction must be endothermic, all right? Endothermic. Now thinking about this, let's just say temperature increases, right? Temperature increases, so LCP wants the temperature decreases, right? So now outside is very hot, the surrounding is very hot, and you want to bring down the temperature. What you're going to do is to do more endothermic reaction, because endothermic reaction is the reaction that absorbs heat from the surrounding, right? If you do more endothermic reaction, you absorb more heat from the surrounding, then the surrounding will have less heat, and therefore lower its temperature, which is what we predict, right? So this would be what we expect to see. The equilibrium will shift to the left, okay? So we will have a net backward, and most importantly, endothermic reaction, okay? So that it will absorb more heat from surrounding, okay, and therefore temperature brings down the temperature, which is counteracting with the change. Okay, so this is how we predict. This is how we predict the change in equilibrium position. Alright, so besides the time and besides the change in equilibrium position, we also have the equilibrium constant. Remember, it is temperature dependent, so now it does change. Now, the change in equilibrium constant actually depends on the change in equilibrium position. So using the same scenario, think about it. Kc is essentially product over reactant, right? Using this example is P over R, right? So if in this situation, it will shift the equilibrium to the left, so you will have more reactant and less product, right? So if you have more reactant, less product, what happened to the Kc? The Kc must be decreasing, right? So actually, Kc decreases in this situation, okay? So this is how you predict the change in Kc, okay? Now, this is a diagram that is very important. They kind of summarize all three changes, kind of, okay? So you notice, same reaction, and there are the blue curve and the red curve. The red curve is hotter than the blue. First of all, the time it takes to reach equilibrium. You see, originally, this is the point where the equilibrium has been reached. But when you have a higher temperature, well, it takes like shorter time to reach the equilibrium. Okay, so this is the first effect. The second effect is about equilibrium position. So as you can see here, because we say that the equilibrium shifts to the left, so you got more reactant and less product. So you see, there are more reactant, okay, this one is higher than this one, more reactant, less product, because the red is lower than the blue, okay? So more reactant, less product. That kind of tells you about the shifting of equilibrium position. And the third one is about the Kc. So again, Kc is essentially product concentration over reactant concentration. So as you can see from the graph here, basically it is this one over this one, right? So if these two are more similar, right, the Kc is more close to 1. But when this one, there is a greater difference. When this one over this one, obviously you can tell should be smaller, right? So that also implies the change in equilibrium constant, okay? Kc decreases. So this is how you predict change of the equilibrium upon temperature change. So again, we have a practice question. Again, pause the video and try it yourself first before looking at my explanation. Alright, suppose you have done it. Let's have a look. Now, in this situation, so when temperature increase, so this is an endothermic reaction. So the temperature increases, we want the temperature decrease. So you want to have more endothermic reaction, and therefore you are going to do more forward endothermic reaction. So obviously the equilibrium position will be shifted to the right, okay? And as you are having a higher temperature, every reaction goes faster, no matter it's a forward or backward. So the time it takes to attain new equilibrium must be decreasing, right? It takes a shorter time, so decrease. And what about Kc? Now, if you shift to the right, you got more product, less reactant. So product over reactant, more product, less reactant. Kc must increase. Okay. Now, the third one. So in this case, we know that the equilibrium shift to the left. So shifting to the left means it wants to undergo more backward endothermic reaction, because the forward is exo. That means the backward is endothermic, right? So how can you make the system to shift to the left? How can you make it to do more endothermic reaction? Of course, by increasing the temperature. If this is hotter outside, the system wants to respond by lowering the temperature and therefore doing more endothermic reaction, right? Now, if this is hotter outside, then the time it takes to get to the new equilibrium is also shortened, okay? And Kc, because it shifted to the left, you got less reactant, more product. So the Kc, you got more reactant and less product. So the Kc decreases. Okay. Now the last one. And this system, You see, when the temperature increases, Kc increases, right? So you think about it. Kc increases, Kc equals to product over reactant. If Kc increases, that means product more and less reactant, right? So more P, less R, it must shift to the right, okay? Must shift to the right, okay? And when the temperature increases and it shifts to the right, this one must be endothermic, right? And lastly, as long as the temperature is higher, it takes less time to reach equilibrium, okay? So this is the answer. Okay, this one, the third one is easier, catalyst. Now, catalyst, again, the definition is something, is a substance that alters the rate of reaction without itself undergo permanent change. In this case, we try to look at catalyst as a positive catalyst. That means it is going to speed up a reaction, Now again, a catalyst speed up both the forward and the backward reaction. So what it does is it shortens the time it takes to reach the equilibrium. Okay? However, since the catalytic effect occurs on both the reactant and the product, and it does not affect the concentration of reactant and product, and therefore it does not result in any shifting of equilibrium position. It has no effect on the equilibrium position. And again, because temperature is not changed, Kc is not going to change at all. So you see from this graph, when you have the catalyst, you reach equilibrium earlier than the one without catalyst. But then everything remains unchanged. Same equilibrium concentration. Okay? Now down here is you imagine yourself as a boss of chemical industry. And of course, you try to earn money, right, from your factories. So how can you design your industrial process? Like how do you set up conditions? How can you make sure everything works perfectly? Now, of course, you have to consider all the criteria that will affect your manufacturing process. The first one is, of course, how fast. The faster, the better, right? The second one is the yield. That means the amount of product. Of course, the more the yield, the better it is. The cost, of course, you want to have as low cost as possible, right? And after that, safety, of course, as safe as possible. However, when we have to design our industrial conditions, sometimes these factors contradict each other, okay? For example, this is a very famous industrial process, the Haber process, which is used to make ammonia, and ammonia is used to make fertilizer, nitric acid, something like that. And this is an exothermic reaction. Now, let's look at the first criteria. If I want to have the reaction go as fast as possible, then we should have a very high temperature and a very high pressure, right? The higher the temperature, molecules collide more frequently, so faster reaction. A higher pressure means a higher concentration of the reactants, so again, increase the collision frequency. Okay, now that would be the best. However, it contradicts with the other three conditions, criteria. If you increase the temperature, it actually shifts the equilibrium to the left, because the forward is exothermic, the backward is endothermic. So a higher if you use a high temperature, the Le Chatelier principle wants to have a lower temperature, so it will shift the equilibrium to the left, okay, which is to do more endothermic reaction. But shifting the equilibrium to the left will result in a lower yield, which is contradicting to what we want. So this is one thing. Another thing is, if you have to have very high temperature and very high pressure, very expensive and also very dangerous, okay? So this is one thing. Another thing is, okay, what about we focus on the yield, okay? If I have like all the nitrogen and all the hydrogen converted into ammonia, that would be the best situation. However, if you want to have a high yield, what you have to do is to lower the temperature, okay? But, lowering the temperature will result in a slower manufacturing process. So again, 2 is is contradicting with the first one, okay? So how do you get things done? So in reality, nothing is perfect. You do not have a perfect plan. So what you're gonna do is to have everything optimized, okay? The best, okay? So you can have an optimal temperature and optimal pressure. So this is how it is actually carried out. So 450 degrees Celsius and 200 atm. So reasonably high temperature and pressure, but not extremely high, okay? So try to compromising the manufacturing process as well as, the rate of reaction as well as the yield. We use catalysts, of course. Catalysts speed up the reaction without spending a lot of money because they are not permanently changed. They can be reused for many times. And the third one here, actually together with the fourth one, is about the design of the reaction container in reaction vessel. The hydrogen and nitrogen, which are what we call feedstock, you can think about it as the reagents, they're continuously pumped back to the reaction vessel. Okay, so that means some of the unreacted nitrogen and hydrogen, they are not going to be wasted. They are not going to simply emitted out to the atmosphere. Instead, there is a specialized pump to actually pump these back to the reaction vessel after all the gas has passed through the vessel. So in that case, we try to recycle the unreacted reagents. And also what we're trying to do is to remove the ammonia as it is being produced. Because by removing the ammonia, then it will shift the equilibrium to the right. So you will have a higher yield. But how do you remove ammonia? Now you need to know that ammonia is actually having a much higher boiling point than the two other gases, because it has a hydrogen bond between molecules, whereas these two only have weak van der Waals force. So it is easier to turn this back to liquid and therefore removed from the system. Okay? So this is how they actually do it. They try to remove the ammonia, okay, by condensation, if you want to put it down as a remark, by condensation. Okay? So maintain a rightward equilibrium position. Unreacted feedstock, recycle back, okay, to avoid wastes and avoid contamination. Okay, so this is the idea. Now again, the last practice question. Again, pause the video to try to have a look, and then let's have a look now. So this is a contact process for making sulfuric acid. How the temperature and pressure affects the rate and the yield. So let me put it down like this. Okay, we have temperature and pressure, and how does it affect the rate and the yield. Okay, so let's just say when temperature increases and pressure increases. Okay, now when the temperature increases, of course the rate increases, right? And when the pressure increases, of course the rate increases. Now, when the temperature increases, the yield will actually decrease because the forward is exothermic, okay? However, increasing the pressure actually favors the yield because increasing the pressure, according to the Chatelier principle, they want the pressure decreases, so they will shift to the side with less gaseous molecule, and that turns out to be the product side. So that will increase the yield if you raise up the pressure. Okay, so down here, instead of, other than using optimal temperature and pressure, two other ways to enhance the manufacturing process. The first one is, of course, use a catalyst, okay, speed up the reaction, right? Okay, and also the second one is we try to recycle, okay, recycle unreacted feedstock or reagent, okay. Right, so this is the idea. So that's it for the Chatelier principle, and in the next video we will talk about reaction quotient. Okay, so see you later.